My name is Ben, and this is my Computer Forensics HD project, an automated fileless malware detection framework using volatile memory forensics. So, starting at the top, what is fileless malware? Unlike traditional malware that writes itself to the disk, fileless malware lives entirely in memory. It uses legitimate Windows tools like PowerShell, abuses built-in system processes, and leaves almost no trace on the hard drive. This makes it pretty much invisible to traditional antivirus tools, which is exactly why it's become one of the most common techniques used by real-world attackers. The only reliable way to catch it is using memory forensics, capturing and analyzing what's actually running in RAM at the time of compromise. This framework consists of 3 Python tools built on top of Validity 3, which I'll show here, which is the industry standard for memory forensics engine. The mem-acquire handles evidence acquisition and chain of custody through cryptographic hashing. Mem-analyze is the core detection engine, which runs 5 different plugins, correlates behavior indicators, and then generates a scored threat profile. And mem-yara, this is a signature-based scanner, which I researched and implemented for the most part, but ultimately found it to be a little bit too noisy for raw memory scanning, just due to the false positives from legitimate DLLs, which is a known limitation that I'll discuss in the report. In this video, I'll walk you through a live attack simulation, demonstrate the tools detecting it in memory, and explain the key design decisions behind the code. I'll get into that now. Okay, I'll now demonstrate the attack scenario this framework was designed to detect. I'm running 2 virtual machines, a Kali Linux attacker system and a Windows 11 target. Both machines are connected through an isolated host-only network, meaning the environment is fully contained with no external internet connectivity. The Kali machine, I've begun by hosting a payload over a local HTTP server, and I've configured a Metasploit multi-handle listener to wait for an incoming reverse connection. So here you can see I'm hosting the HTTP server, that's where the payload is being hosted, and this is the MF console multi-handle HTTP reverse connection. On the Windows virtual machine, I'll execute a PowerShell download cradle, and this is a classic fileless execution technique. It's commonly used in real-world attacks, pretty much solely because it avoids writing a traditional executable to disk. The PowerShell command retrieves the payload directly from the attacker machine, downloads it in memory, and executes it in process. There's no PE file dropped into the file system or anything like that. Many traditional signature-based antivirus solutions have very limited visibility into this kind of activity. Back on the Kali, let me just first execute this command here. And now we're watching on the Kali. You'll see a meter per session that successfully opens, and we're going to look at the PowerShell, and there you go. Okay, and get user ID, and while that's running, we're going to capture the memory dump. At this point, the malicious payload is running entirely in memory, and there's no standalone execution stored on the disk, which significantly reduces conventional forensic artifacts, and it makes most post-compromise detection more challenging. Now that I've executed several commands within the session, it's generated additional runtime artifacts in memory, like activating network connections, ejecting memory regions, and all that, and just general suspicious process activity. Immediately after, on the Windows machine, I'll acquire the full dump using winpmem like I have here. You can see the command is successfully unloaded, and then I'm going to move that to my Kali machine. The memory image captures the current complete state of RAM at this exact point of client time, including running processes, loaded DLLs, active sockets, command history, injected code regions, all of that, and remnants of the in-memory payload itself. Once that's back in the Kali for analysis, we'll process it through the detection framework. And the framework will then phase the memory image, extract forensic indicators, and identify behaviors consistent with fileless malware execution. Okay, MemAcquire is the first tool in the framework. It handles forensic acquisition and a chain of chain of custody. I'll run it against our MetaPrinter dump down here, as you can see, and while that does its thing, I'll walk you through what it's actually doing. The core function is the calculate hashes function, that's here. It opens the memory dump in binary mode and reads it in 8 kilobyte chunks, rather than loading the entire gigabyte file into RAM at once, which would obviously crash the system, something I learnt the hard way. As it reads each chunk, it simultaneously updates both an MD5 and a SHA-256 hash. The reason we calculate 2 hashes is that MD5 is fast and widely recognized in forensic workflows, while SHA-256 is cryptographically stronger and more tamper resistant. Together, they give us just a standard robust integrity verification. The create metadata function down here then packages everything into a structured JSON file, recording who ran the tool, when, what file was processed, its size, just both the hashes. This is, our chain of custody record. If anyone questions whether the evidence was tampered with after acquisition, we compare it with the hashes. And if we scroll further down, you can see the tool has worked fine. We've got the MD5 and SHA-256 printed on the screen, and metadata JSON file which is saved alongside our dump. That JSON file is our forensic receipt for the receipt of evidence, for the piece of evidence. So we can go to memory dumps right now. And as you can see, it's MetaPrinter active metadata. We can cut that out. And ta-da! Everything's very neat. We've got the timestamp, the analyst. Obviously, I didn't enter my name for this, that's fine. The tool, and the dump name. We also got the file size, the absolute path, our integrity checks, and any notes that we add. This is hard-coded at the moment, but that can be changed. Outside of this, we also have the mem analyze script, which is about 1,500 lines long, which I'll get to next. Okay, the first thing the mem analyze does is run 5 volatility-free plugins against the memory dump. And the function that handles this is called run volatility plugins. That's this one here at the very top. I've put comments in the code so it explains it, but I'll go into more detail. Rather than trying to re-implement what volatility already does, this tool simply calls it as a sub-process, essentially running the same command you type in a terminal, but from within Python. And then it captures the output and passes it through for phasing. And there's a 10-minute timeout on each plugin call, which sounds long, but when you're processing like an 8 GB raw memory dump, volatility genuinely needs that time. Without the timeout, a hung plugin would freeze like the entire framework indefinitely. The 5 plugins run are plist for the process list, a PS tree for parent-child relationships, command line for command line arguments, netscan for network connections, and malfind for detecting executable memory regions, which is the core injection detection mechanism. Once the plugins run, their output needs to be passed or phased through structured data, and the analysis engine can work with. This is where things get pretty tricky, because volatility doesn't output JSON, it outputs human-readable tables, and the formatting isn't always consistent. So the phase volatility function, which is this one here, or table, function handles this by first detecting whether the output is tab separated or space separated, and then it finds the header row by looking for keywords like BID or offset and mapping each subsequent row into a dictionary. There was a lot of blood and sweat and tears that went into this part. There's also a regex fallback for phaser for cases where the table phaser fails, because in practice, volatility's output format can vary depending on the plugin version and the memory image being analyzed. Building in that fallback was a pretty important, robust decision. Malfind gets its own dedicated phaser entirely because, unlike the other plugins, it doesn't output a clean table. It just outputs blocks of data per process, including hex dumps and disassembly. So the phase Malfind output reads it block by block, grouping detections by PID and all that. This is what I was talking about before. Phase the data rows, puts them into a list. Phase plist output, it's just the output text. And this is the regex I was talking about. Takes the output text, again, the fallback phaser in case the plist is using regex, and then PS3 command line. I've set a phaser for all of these, but they all use essentially the same function except for Malfind, which obviously detects it block by block, save last block. And that's all very good. But now we sort of get closer to where the real forensic thinking comes in, and honestly probably the most important decision in the entire framework. Volatility's malware function plugin works by flagging any process with executable writable memory regions. That's called RWX memory. The problem is that on any normal Windows system, dozens of legitimate processes have RWX memory for completely valid reasons. Google Chrome uses it, JavaScript JRT complications, the net runtime uses it for native code generation, and Windows Defender also uses it for scanning, right? So on my first version of this tool, Malfind was generating over dozens of reports and alerts on completely clean systems. That's completely useless in a real investigation, right? So if everything gets flagged, nothing is meaningful. That's where this comes in, which is the isLegitimate system process function. It implements a whitelist of good known processes along with the reasoning for why each one legitimately has RWX memory. But, and this is the critical part, whitelisting alone just isn't enough. The high-risk processes that should never be automatically trusted, even if they're running from System32 or PowerShell, command line, etc. These are all legitimate Windows tools, but they're also commonly abused by attackers for fileless techniques, which is what my tool is all about. So the logic is, if a process is on the whitelist and has no other suspicious indicators, skip it. But if a whitelist process also has suspicious command line arguments or unusual network connections, it gets flagged anyway, because that combination is genuinely interesting. So here we see legitimate processes. We put it into a dictionary of all of the legitimate processes that I was getting flagged before, the net framework, Windows scheduled tasks, all of that. And then we say, if it's a legitimate process, return true and skip it. Otherwise, trusted paths, etc. And that's very cool. And this is where the analyze suspicious command lines comes into play. This is what the version 3.1 enhancement refers to in the tool name. It's the difference between a noisy scanner and an actual detection engine. So with the whitelist handling false positive suppression, the framework then runs 4 separate analysis passes, each looking at different dimensions of suspicious behavior. The very first is analyze suspicious command line. This scans every process's command line arguments against a list of regex patterns, each with an assigned severity score. For example, the -enc flag, indicating an encoded PowerShell command, scores 8 points. It's commonly used in obfuscation and all of that. And then download string scores 9, and then the word mimscats scores 10. Importantly, scores accumulate. So a process using encoded commands and downloading a remote script and invoking like an expression gets all of those scores added together. This is why the MetaPreter processor scored so high. It matched multiple value patterns simultaneously, which I'll show you soon, the output of this in a second. The second one is analyze parent-child relationships. This checks for process family trees that shouldn't exist. Word spawning PowerShell scores 9 points. That's a classic macro attack. And then there's Chrome spawning command cmd.exe or svc host spawning PowerShell. These are all defined pairs that indicate something has gone wrong in the process hierarchy. The tool also catches orphan processes whose parent PID no longer exists in memory, which can indicate a process that tried to hide its origins. These are all behavioral indicators, much more significant. The fourth and most sophisticated is probably analyze code injection. Oh, actually, I'll briefly touch on, this is the network connections one. This flags processes with suspicious network activity, specifically things like PowerShell with an established connection. So connections using a reverse shell ports like 4444 and basic utilities like Notepad or CMD that simply should never have network connections at all. That's what this looks for. You can check for specific ports. That's what that is. Add 7 points, 8 points if it shouldn't have a network connection. All of that noise. This is the most complicated one though. This was hard. This is where all of the previous analysis feeds back in. Rather than flagging RWX memory region independently, it requires correlation. A process needs RWX memory plus at least one indicator from the other three analyzers before it gets flagged for the code injection. That's the key architectural design or decision. There's no single indicator that triggers an alert on its own. It's a combination that produces a high confidence detection. And you can see exactly this playing out in the MetaPreter result, which I will show you in a second. But the final stage is the correlate indicators, which pulls everything together. You can see it's asking all of the checks at the top here. Correlate with other indicators, which pulls everything together. So every process that triggered at least one indicator, it builds a complete picture. Process name, parent process, command line, every indicator that fired, and a combined total score. The severity classification is applied based on that score. So critical is for anything above 20, high is for 12 to 19, medium is 6 to 11, and low is anything below that. So the reason the score-based classification rather than simple pass/fail is that real investigations are rarely black and white. A process with one minor indicator might be worth noting, but not necessarily acting on it immediately. A process with 7 correlated indicators across command line, network, and memory is something you investigate right now. The scoring system reflects that nuance. So the framework then outputs 3 strings, a full JSON analysis report containing every process, every indicator, and all the raw plugin outputs for a complete forensic reproducibility, as well as a separate threat profiles JSON containing just the suspicious findings for quick triage. And the terminal dashboard, which we have seen down here in the output, just gives a very immediate visual summary of what was found. So together these outputs were designed to serve 2 purposes. The dashboard for quick triage during an incident, then the JSON reports for detailed post-forensic documentation that can be handed to a broader investigation team, for example. And that's the complete framework, from memory acquisition to through to behavior correlation and to the classified or threat output. You can see here it's caught the critical rating, 96 points in total, and a quick dashboard on what was found. You can see it's caught the exact command run from the Windows virtual machine that injected the payload for the reverse shell in the first place, which is all very cool. And again, this is in the threat profiles. everything that was specifically stood out, like a remote script download, the web client Gradle, the PowerShell with an active network connection. All of these were given a score or points, and obviously code injection is the biggest deal here, which leaves us with a score of 96, which is very cool. But yeah. To summarize what this framework demonstrates, given a raw memory dump from a compromised Windows machine, it can automatically identify a meter-preter reverse shell with a confidence score of 96 out of a possible 100, and then classify it as critical severity and produce a detailed forensic report, all without any prior knowledge of what the malware was present. The biggest challenge throughout this project was definitely the gap between planning and reality. Far less malware samples that produce clean, predictable forensic artifacts were genuinely hard to come by, which meant pivoting to a controlled simulation with approaches like using Metasploit. That pivot actually taught me more about how these attacks work too, in practice, than following the original plan would have. And above all was probably the difficulty in coding this. I started with very little programming knowledge, and I needed hours, days, weeks of effortful pushing through, and it's definitely a good result, I think. I didn't do this without the help of AI or something. That was a big help in helping me break down the more complicated parts of this, but it's brought me a long way. The most valuable thing I learned was probably that detection is fundamentally probably a correlation problem. Any single indicator like RWX memory or a suspicious command line, an unusual network correlation, all of that, they can have a legitimate explanation. This was a constant reoccurring theme throughout this project. There was many times when I was getting false positives where it just wasn't getting what I needed. So when it's multiple indicators that appear together and have the same process, that you have something worth investigating. That insight is baked into the architecture of this tool. So for a HD project, this represents a working end-to-end forensic framework built on an industry standard tool with genuine design decisions around false positive reduction that reflect how real SOC tooling actually works.